Good afternoon, ladies and gentlemen. We are Team 16. We're part of SkillCourt as well. My name is Johnny Lewis.
Jonathan Perez.
John Conley. Erim Gokce.
And we were tasked with developing a rebounding sports training structure. Now, for our problem statement, we wanted to provide professional grade training for sports enthusiasts of all skill levels, and we wanted to specifically design and manufacture a rebounding structure that would be able to integrate computer vision. For our motivation, we wanted to facilitate training of the fundamental skills of competitive soccer at all skill levels and provide soccer enthusiasts with a sports training structure that was able to adjust the angle of impact and collapsible, as well as track the play. For our literature survey, we looked into a few strike location detection sensors, piezoresistive sensors, load cell sensors, tensor sensors, and electromechanical toggle switches. For the tensor sensor, it allowed output configuration as well as could be tested against overloads. It had a range of about 10 to 500 newtons, but unfortunately, it did not meet working. For the infrared LED receivers, this would be able to track the player depending on the emitter that they would have on them. These receivers work together with connecting the player to the actual frame and would provide us with the goal of being able to measure the velocity of the actual ball. We finally looked into front-facing cameras that would be able to use color tracking. This would help in terms of which color t-shirt the player would eventually be wearing, as well as also give us the goal of determining the velocity of the struck ball. These were chosen over the IR sensors because of the geometrical restrictions provided. If you can see here through our survey of related standards, all our parts and everything used were ASME and ASTM qualified. Our aluminum 6061 worked for the rebounding frame itself. We use monofilament nylon cores for the rebounding mesh up front, screws and fasteners to put everything together, and of course CAD for the modeling. At first, our project objectives were to achieve frame targeting, to be able to track the player, have a 90% rebounding effect of the momentum, be able to be affordable, safe, collapsible, and of course compatible with the codes that SkillCourt has already put in place. But for our prototype design itself, we wanted to make sure that we achieve the 90% rebounding momentum, be able to track the player and or the ball, as well as be able to use the integration of the electromechanical toggle switch and have the rebounding pad itself be able to rotate 360 degrees. Our prototype constraints, we wanted to be able to emulate the actual game of soccer, but by making the rebounding pad about a rectangular shape to imitate a soccer net itself. We wanted the system to be able to be powered by electrical outlets that would be out on the soccer field, weather resistant of course, and be able to, for our sensor to be able to withstand high sunlight exposure as well as financial environment.
So here's our chosen design, which you can see physically here right next to John. As you can see, this is the aluminum frame, and in the back the base is steel, and this is the monofilament nylon mesh right here. In the picture you see multiple toggle switches, which are the bars that are right behind the mesh. And then we changed this a little bit from our old design, but knew that it would be durable and weather resistant and provide just as much rebound. And fortunately on this model right here we don't have the camera stock, we'll explain about that later, but on our model that's where the camera stock would be. So in order to make this a sound project, we had to do some simulations on key points that we thought had high stresses, such as the arm right here at the connection. And we determined the force that we would apply to it due to research and literature surveys. The amount of force a professional soccer player can kick is up to about 225 pounds of force. So to be conservative and take into account the weight of the actual frame, we decided to use 500 pounds of force, which gave us a factor of safety minimum of 2.32. And to add even more rigidity, we've added welded joints at the corners. And we also want to take into account what would happen if the ball was to strike the frame at this force, making sure it didn't dent. So we have a minimum displacement of 0.002 inches, which provided us the satisfaction we needed. And we also did a simulation on the ball striking the mesh net, making sure that it wouldn't snap. because we didn't have much experience with this material. So we came out with a factor of safety minimum of 1.35, but we also wanted to do a physical test because the manufacturer of the actual the nylon only comes with a tension test, not with the ratings that we were looking for. And initially in our design, we were going to weld a shaft to the plate that's attached to the arm, which I'll explain a little bit more in depth. We had figured out that the moment of inertia that needed to rotate the assembly around the center of the axis was about 20 foot-pounds. And here you can see the displacement and the factor of safety of 15, which provided us a safe enough answer to be able to use that option, which was changed later, but we'll go into details later. So here's the base assembly. You can see here on our actual model, and the actual aluminum Go frame with the mesh net and the connection assembly right behind it. Unfortunately, we outsourced our welding to a vendor and provided them the correct documents needed to do the welding, but they unfortunately welded it backwards. This front face is supposed to be on the back side, so we had to compensate for that in our design when we were actually doing the construction and change it just a little bit. Here's the arm assembly before we welded the shaft to the stainless steel plate, and then here's after. You can see a lot of browning around the shaft. Underneath the shaft, right up against the plate, is a collar, and the collar was welded on a little bit crooked, so it made a lot of friction on the table when it turned against the top of the assembly. So we had to change that, and also there was a lot of misalignment with those as well. And we also tried another option, turntable option similar to a Lazy Susan, and you can see from the picture right here that the material is really thin, so it was going to fail due to strength. We tried it as an option because it was a really low cost option. We were trying to go that route, but we weren't able to use that. It wasn't viable. There was a lot of misalignment and precision with the shaft and the table. So our final design, we came up with a flange mount shaft collar attached to an aluminum plate sitting on a roller thrust bearing, and it's paired with mounted sleeve bearing, and it was able to make our assembly rotate perfectly. Here's a picture of our motor. On the top right of the motor, you see the torque limiter. It allows for overshock or over torque of the motor and to ensure safety of the player. And on the right, you can see the mounted sleeve bearing and the roller chain assembly with a 48-2 sprocket and a 9-2 sprocket connected to our 12-volt motor. And on the bottom of that picture, you can see our slip ring, which is used to connect the electrical components to the hollow shaft that will be going to the camera stock. Here's some of our electrical components. The electromagnetical toggle switch, which we have right here, we designed ourselves. And then we have a converted computer power supply that we use for testing. The actual model would have a battery, which we do have, but we use that for testing. And we have an embedded LED right here on our model. This is the final prototype and the physical design itself.
So we were concerned with 4 main components, and we performed 4 tests for those components. Initially, our rotational capabilities and our rebounding capabilities, as well as our player tracking and electromechanical tolerances. So for our rotational testing, we wanted to ensure that our motor would output enough torque based off of the torque ratio we have with our sprockets and turn the frame 360 degrees. We also wanted to ensure that in this dynamic system, our electrical system would be able to withstand any shocks during testing. Here is our electrical schematic. It's kind of blurry. In the middle is our converted power supply, and there's the motor that we use. So here's a video of our rotational testing. When we were testing it in the clockwise direction, it rotates at a suitable speed. We're manually controlling the program that we wrote. Now when we turn it in the counterclockwise direction, you see there's some friction and it stops. So we increase the current supply to the motor, and it's kind of hard to see here, but what happened was our motor driver burnt out. All the electronics on our motor driver started smoking and came apart from our motor driver. We initially thought we purchased a motor driver suitable for our needs. Currently, this happened last week, so we're contacting the vendor and trying to mitigate these issues. Next, we moved on to the rebounding test. We wanted to ensure that the mesh would not fail during testing. So this was a static test, and we measured 3 different locations 5 feet apart and tested our rebounding net. As you can see, the velocity before and after the impact of the net is what we're interested in, and the degradation of velocity. In our 5 feet test, we're almost at 90% velocity ratio degradation, and then 95% at 10 feet, but at 15 feet it drops off. And that is primarily due to us not being good soccer players and missing our kicks every now and again. And that's kind of why the camera stock broke, is because I missed a kick during our testing phase. So here is a video of our rebounding test. As you can see in the testing, the frame has some vibrations in it. To mitigate these issues, we plan on, for future development, we plan on including tensioning cables from the corners of the frame to the corner of the arm connection to solidify the arm and reduce any vibration. Next slide, please. So next we did the player tracking, and we use OpenCV for our testing. We set a color view. In this particular instance, it's blue. And then we found the centroid of the point of the player wearing the blue shirt. And then once that centroid was located, when they moved, the centroid had a change in distance. OpenCV was able to determine that distance and relay to the motor driver, move this much, these many steps in this direction, these many steps in that direction. That was our first iteration. Next slide. Here we have a video of our second iteration. As you can see in the top right corner, that these arrows are determining which direction the motor driver is supposed to go, and these 2 horizontal lines or vertical lines are our tolerance, so that when the player is within a certain distance, the frame doesn't jerk back and forth trying to find an exact point. Finally, our electromechanical switch. We were successfully able to embed it in our mechanism and test it a few iterations before our driver failed. We were just trying to prove our conceptual design. This was designed by one of our team members, and we wanted to ensure that it was struck and depressed during a strike, and then it reverts back to initial position. So that was successful. So to sum up, our player tracking was successful, but we broke the mechanism holding it. The camera still functions properly. We just need to purchase a stronger flange to mount the stock. That was what failed during impact. Our rotational capabilities were unsuccessful because our motor driver burnt out, but our rebounding capabilities we feel were a success. And for the switch test, it depressed enough suitably for us, but the only issue we have with it is including more iterations and having a finer mesh to locate the ball strike more accurately, and fatigue testing after hundreds of thousands of iterations.
In the design stage, we had 2 initial cost lists. We had one threshold to stay under, which was $1,500, and then we had a predicted cost, the cost which we expected to incur by the time it was built. In the end, we did stay under that $1,500 budget, but we did go over the predicted cost by about $60, which is to be expected. This is just a summation of our team responsibilities. In the interest of time, I'm just going to glance over them. And this is our Gantt chart. From October until May the 9th, we adhered to the schedule from beginning to end. And for risk assessment, the highest risk would be if we were to lose complete control of the mechanism and we were to spin erratically and out of control. To mitigate that, we installed that blue torque limiter, which would limit the torque to 25 foot-pounds, which would mitigate some of the risk with that. Also, a physical kill switch to be installed on the mechanism itself, and one in the application in case it's too unsafe to hit the physical switch. Below that, the next risk would be if the player were to be physically struck by the frame as it's rotating. The solution to that was not too complex. It would be to install proximity sensors on the frame so that they can detect the player is in the rotation bounds and then halt itself before the contact is made. Below that, if any loose articles or fingers were to be caught in the rotation components, mitigating that would be to increase the distance of the shaft to the plate edge and make that large enough that any clothes or articles can't be caught in that as it's spinning. And then the lowest risk we deemed was if the power supply just dies and then the frame keeps on rotating and doesn't halt when it's supposed to, which would be circumvented by momentum and friction and eventually coming to a halt. As far as feature work, SkillCourt aims to further test the electrical system and the rotation components. The motor driver would either be swapped and tested further, and the extension wires would need to be changed out. The complete addition of the linear actuator is to facilitate the rotation, the tilting of the frame as a response to the player and getting the correct angle to rebound back towards the player, as well as integrating the code to relay back the real-time camera tracking and response from the frame as it rotates, as well as improving the dynamic stability of the frame. As you saw, there was some vibration in that video. To mitigate that, SkillCourt aims to plan to install taut wires in an X fashion to absorb the vibrations and basically improve the dynamic stability. And then further testing of the toggle switch would be required, which would relay the real-time velocity and accuracy statistics back to the player. In conclusion, the prototype did fail during the rotation stage. The camera stock was also broken into a high-velocity impact kick. However, we were able to integrate most of our design goals, and the hindrances that arose were enough to have us not meet all of our goals by this date. However, the design we present is a very viable model for future teams to build upon, and we believe it's a good foundation. And this is our poster, and if you have any questions, I'm happy to answer.
You had made in one of the earliest statements, this is something about systems should be collapsible.
Yes.
How is this collapsible?
This is a concept design, so the model that is aimed to be presented in stores and sold to consumers will be fully collapsible, but this is a first stage.
And how would you do this to make it collapsible? What would you do to this to make it collapsible?
Well, the parts would need to be easily removed, as in the fastener locations, and then make it intuitive to have it constructed. Not so many parts, but enough that it could be fit into tight spaces.
Okay, and again, talk to me about weather resistance and safety in your commercial application of this. How would you do those two things?
Safety.
And let me just throw the question, one to you and one to you. Okay, you take the weather.
For the weather resistance,
Yes, please.
we plan on actually providing a coating for all the metallic parts of our project, as well as wrapping it with like sheet metal. So this way, this is enclosed in an encapsulated place with a small door that you can access the components on the inside, which would make it weather resistant.
Okay, and safety?
For safety, for initial prototype, we have the torque limiter. So if anybody was to come and stop the frame's motion, the torque limiter will disengage and won't destroy our windings. One, and two, it'll stop the frame from moving and hurting the player.
And what's it set at?
25 foot-pounds.
25.
For future teams, we're planning on including ultrasonic sensors for proximity reasons. So if someone comes in the way of the motion of the frame, it'll kill the power. And then, like he said, if none of those work, there's going to be a kill switch on the SkillCourt app.
What about pinch points?
Pinch points for our prototype, there's a few jagged edges, but
That between the two moving mechanisms.
between right here,
Yes.
during playtime, nobody should approach any bit of this.
But they will.
During
That's the
testing,
question.
we're going to be having a professional test, so they're not going to be touching it. For final prototype or final construction for a final mechanism for sale, these pinch points will have to be mitigated and resolved.
Okay. And your question for you on the toggles. Why did you decide to put them on one side?
Well, this was just specifically just for this model. We did, actually, if you looked at our proposed design at first, we were going to put multiple toggle switches, but for the prototype itself, we decided to put one toggle.
Then why did you put it where you put it?
Well, we put it where we put it. Well, you could have put it on any side, honestly. That was just more like a...
Because I would have thought the deflection in the middle of the system would have been larger than the
We
deflection
didn't want
inside.
it to get damaged as well, if for any...
Part of that is due to the design things that we had to change when this was welded incorrectly. Actually, this is supposed to be recessed into this space, but unfortunately, due to the space changing, we had to add these mounts here. So we put this here on this side, mostly for the spacing of the ball. All those spacings that you see from the different toggle switches are about a ½ inch smaller than the ball, so this way we can know that it struck this middle section. And we actually put it here just to see how far, just to test it in hitting the side of the face and actually hitting this.
Okay, thank you.
Yes.
So I have a couple questions for you. First, I would, next time, in the future, make sure there's consistency across the teams. The team before you said that a soccer player can kick up to 300 pounds. Now you used 225 for your factors of safety.
We used 500, but that was
Use 500 for your design,
Mhm.
but you used 300 as the force being measured, or the limiting force in your equipment. So just make sure that there's, or I'm sorry, 225. Make sure there is consistency across the projects. Second is I would like to see a cyclic analysis. This thing is going to be going back and forth. You did do the static analysis on the structure, but there's nothing that tells me, after 100 hours, I'm going to have to change the motor, because it looks like a very heavy structure for that motor to move. There's, that motor's got, and the structure itself, it's going to have a lot. And third, we saw a similar analysis with the previous team, where you're doing a distributive load on the center of the net, not on your limiting locations, such as your corners or even the structure itself. So that's something else you need to consider. Don't just go with most likely scenario, assuming a pro is going to hit it in the same place every single time. As one of your teammates saw, you can sometimes hit this in places where you never thought you could hit it. So don't assume best case scenario. Always test best case, but also test worst case scenario.
Thank you.